Right, good afternoon, everyone. I'm awake. Can you help me wake up? Can you shout graphs, yay? Graphs, yay! Bit louder? Graphs, yay! Fist pump? Yeah, all right, cool. Hands up if you like, or if you don't like audience participation. Cool. That's the end you'll be glad to hear. Cool. So, hi, I'm Chris Hoult. I've been doing PHP since 2004 and being paid for it, the fools. I'm a senior software engineer at Datto, and we do backup devices and stuff like that. I do mostly web, kind of web API type stuff there. And prior to that, I was at DataSift, selling all your Twitter and Facebook data, and LinkedIn. And at Time Out Digital, building platforms for magazines and stuff like that. I'm also the founder and co-organizer of PHP Berkshire in Reading in the UK. So if any of you are going to be in the UK in the near future, third Wednesday of every month, we need speakers, please talk. I also act. I also shave. I also reuse my jokes from yesterday. How many people were here yesterday for my ethics talk? I didn't put that many people off then. Good. This one's a bit of a lighter one. Graphs are everywhere. Thank you. Jokes land. I like it. Not much code's going to be shown in this talk. I apologize now. I've got a couple of links to a couple of pieces of code, but I just want to kind of get the general basics of what graphs are and a couple of fun aspects of them, and just try and communicate to you that graphs are cool and graphs are interesting and useful, and maybe if we started thinking in graphs a bit more, we could solve problems in different ways and elegantly and so on. So, first off, the 7 Bridges of Königsberg, history lesson. Leonard Euler? No one gets the joke over here. Cool. In Prussia in 1736, he was a mathematician, bit of a philosopher, and thought, how can I get across the city, across all these wonderful rivers, by the 7 bridges, how can I get to each island by crossing every bridge without crossing the same bridge twice? And so he did what a mathematician or a philosopher would do and started boiling it down to, well, the shapes of everything doesn't really matter. What matters is we know we're on an island or on one side of the river, and we know that the connections are there, the bridges are there. So what we can start thinking of and looking at this is a graph. This is the kind of the foundation of graphs. So we have nodes. We might think of them in physical sense, so locations in Amsterdam. We might think of the connections between them as edges, how they're connected. They might just be, this is connected to that, or you might have metadata attached to that. This is the bridge to there, or I'm a friend with that person, and so on. When we have a number of edges per node, we count them, and we call that the degree of the node. So you can see in the middle island had a degree of 5, the north side, the south side 3, and the other island there in the east, because I can do directions at the moment, is also 3. So this is an example of undirected graphs. There's nothing stopping you from going over the bridge and coming back the same way, because it's a two-way bridge. If we had one direction, if it was one way only through there, it'd be a directed graph. You could only go between these 2 islands here in that direction, for example. So because Euler was trying to cross everything by only using a bridge once, they would be directional. I mean, he has the advantage of, or had the advantage of, choosing which direction he traveled over them, but as soon as he went over them, they're effectively directional. And one thing that he discovered was it's not possible. He just discovered that you cannot do this, you cannot find a path through this. And the reason is quite simple. To get into and out of a node, you have to have one way in and one way out. So that means that if you want to start at one and end at the other, and only ever visit each one once, the only time you could enter or leave once could be at the start and the end. So the only graphs in which you could do that would be is if you have 0 or 2 nodes with an odd degree. So failure, but founded the idea of graphs. I've got lots of points on here. If you want a copy of the slides, we'll pick it up later. So what can we do with that? I mean, it's a good example of pathfinding, but how can we find our way through these graphs? There are two kind of ways. If we want to get from A to B in my imaginary green and red thing, we've got depth first and breadth first. So depth first. You start at A, and I can use my laser here, I'm very happy. You start at A, and what you can do is you start just traversing the tree. So you go, I'm at A, I'm going to follow the first link I've got, and from there I'm going to choose a link and keep going. And what you see is we've actually got, this is called a cycle, because you've come back to where you started. And you can keep going through, and you decide which nodes have already been traversed. So if you say, I've already visited this one, you know you can backtrack as you come through, and basically follow everything you can until you find your way. Now the advantage of that is, eventually you'll hopefully find one of the shortest paths between there, because you're checking, you're going one step at a time as you go through. The downside of that is you can get very lost. You can keep going for a very long time if you've got a huge connection of all these things. But we will get there having traversed the whole graph eventually. If you've ever solved a maze by going through, starting off at the beginning, taking every left turn until you get back to where you've taken the turn before, and then taking the next left turn, it's that kind of thing again. So what can we do with this? This is my favorite bit, and I put it at the front, and I kind of thought I should leave it at the end, but it's fun. I'll wake you up again. We can take sentences. Our language is actually a graph. Well, it's not actually a graph, but we can take our sentences and model them as graphs. So the cat sat on the mat. If we consider them, each word is a node. And we can say we have a single direction travel through this graph. We can say mat follows the, follows on, follows sat, follows cat, follows the. And if we just add a couple more nodes to this, we can add a start node and an end node. Now this is a bit boring until we add in the dog sat on the rug and start adding these connections here. So you can see how if we keep adding more and more sentences, the bag was on the carpet, it gets to the end, we can start building up this kind of connection that has multiple paths from a start node to an end node. I feel like every time I turn my head left, you can't hear me. I'll just keep talking in that direction and do that. So what we can do is, to generate a different sentence that we didn't put into the system before, we can just start at the start and find our way one at a time randomly through there. So start at the start, the dog, okay, we've randomly chosen that, sat on the mat. Oh, we didn't put that in. It might be total gibberish when we do this. I promise you, it sometimes and generally is. But you can see how we've actually taken our grammar, the emergent grammar of the words that we put in, the sentences we put in, and we've modeled that grammar as a graph. We've decided what words can follow each other, and even though we don't know what a noun is, or a verb, or an adverb, we can still generate unique content, and trust me, it can be unique. So, the fun thing about this is you can generate fun things. So how many people here have heard of the Daily Mail? Yeah. I try not to give it my advertising dollar, but there's a certain style that comes with their headlines. And hopefully, in theory, we might be able to generate some headlines that maybe, quite possibly, they've come up with their site. So if you do have a mobile phone, feel free to play with this, choult.com/DM. That bit.ly link, I'll try and find a better way of putting that out there, but that's where the source that takes the data in and constructs a graph and then walks it, and you can kind of see where it's going. But when I was constructing the slide deck, I had a bit of a play myself and came up with some wonderful gibberish myself. So I came up with, North Korea fires a 60-foot well in the first job, says he was shot dead. His emotional visit to long-forgotten 1846 Wild West settlers who won by ISIS attack. It has to be in capital letters. It just has to be. Michael Phelps gets his friend's Japanese Akita dog. And my favorite, it's the very touching story about the awe-inspiring moment America's Got Talent act goes gluten-free with her brother. Absolute gibberish, but every now and then the laws of randomness means that it could be in the Daily Mail. How many people here are Dutch speakers? I'm very sorry if you get offended by anything next. So Raphael in the front row here suggested I did something with a local source, so 85. If I take their headlines off an RSS feed, I can feed that into my same thing, copy and paste code, all the best. It's the same underlying bits of code, but you can play with it now, choult.com/85, and with the very small amount of data I've gathered since I started scanning the feed, I've actually picked up. I'll let you read that. I believe it's a woman rode her scooter into the water and now she's gone to youth court for what she's done. Something like that. Or that one. And you can see where we started off in the same place. A woman was driving with drugs money. I think did I get that right? Oh, thank you. And a taxi driver doing things with overweight people in the Northwest. So this is all coming from live headlines being fed in and going into that. And it is a bit of fun. This is an example of Markov chaining as well, if you've heard of that. So basically, we're building a graph in the way I showed, and then as we come to exit each node, we choose a random connection on the way out and keep walking until we find a start. Some of those sentences are very long. So, breadth first. Breadth first is a different way of doing it. Well, instead, we start from A and go to B, and we go and visit every node that is one distance away. And if we haven't found our path, we then go from those nodes that are one distance away and go one distance away from them, or follow every connection out of those. So haven't found B yet, haven't found B yet. So now we're at depth 0, depth 1, and depth 2. So from depth 2, we then finally go, and we found B. Downside is, we've found the whole thing, but we know that our shortest path is one of these two paths here. So we might have traversed the whole thing and taken a long time and fit it in memory and whatnot, but we find it in the end. What fun things can we do with that? Kevin Bacon, look at those eyes. Look at those, yeah. So, who's heard of the Kevin Bacon number? Or the 6 degrees of separation, the 6 degrees of Kevin Bacon. What you can do is you can connect, or you can at least try to connect, anyone in the world with anyone else by 6 degrees of separation. So you go from one person to a friend to another friend to another friend, and hopefully within 6 of those hops you find the person that you're trying to connect them with. People have turned that into a game with Kevin Bacon. How many Kevin Bacon movies have had lots of people in and connect all that up? So yeah, actor A works with actor B on movie 1, B worked with C on 2, and so on. So Pierce Brosnan to Kevin Bacon. what can we do? He does have a Bacon number of 2. There is a website, and hopefully I put it in the slides, but otherwise you can find it quite easily of someone who's built this off IMDb data. He was in After the Sunset with the sadly lost Chris Penn, who you might know from Reservoir Dogs. He was in Footloose, which starred Kevin Bacon. Yay. So we've had a Kevin Bacon number of 2. But you can imagine how we kind of search every film that Pierce Brosnan was in and find all the actors in there, and search from each of those actors and find all the films they were in to then find, oh, we found Kevin Bacon. Kind of makes sense? Yeah? Cool, I've not lost all of you. This is quite a big graph potentially to walk with IMDb. There are, when I wrote the slide, there's probably more actors now, but 3 million plus actors, 2 million plus movies, and you have to fit a lot of that into memory just to have much of a chance of doing it quickly. The other thing is, if you use a depth-first search, you could just be there playing this game with your friends the whole way through. Well, he was in that, and she was in that, and they were in that, and keep going and get lost and never find Kevin. Whereas if you use a breadth-first search, you will find him, even if it takes a while, you'll still find the shortest hop as you can. One thing that you'll find as well is breadth-first searching is used in IP routing as well, but we have information about the nodes on the, as you hop through different routers as you go through, so you have information as to how far away certain hops are there. You're building your tables of distance from different places. Yeah, it would just get lost. A different approach such as Dijkstra's algorithm or A-star search does do better. So I'm going to show you Dijkstra's algorithm now. I couldn't explain to you A-star search, and having found a mistake in my slides earlier today that I have corrected, I'm now doubting myself on Dijkstra's algorithm. So please don't heckle, come up to me and tell me discreetly afterwards, you got that wrong, if you know it. If you don't, I'm great. I'd have done this in Amsterdam, but I didn't have enough time because I don't know how to do this kind of stuff efficiently. So if you know London, London has several bits of it that are old and therefore have lots of different connections. Doing this in New York, no. So we can think like Euler. How can we get from Piccadilly Circus down to Trafalgar Square, and specifically Charles I statue and that kind of area down there? Well, we can think of the intersection of each road as a node. So every time we hit a place where roads cross or touch, that's a node. We can think of the roads between them as the edges. So these are connections. Looks just like a map, doesn't it? Graphs are everywhere, that's the point. And what we can do then is arbitrarily, I haven't done this accurately in any way, but we can look at those lines and go, well, that's a bit 2 and that's a bit 1, and start thinking about how far it is between each one here. And this is an example of a weighted graph. So not only do you have the connections, not only do you have the degrees of each node as you go through, you also have an understanding of the cost of moving between two. And this is particularly useful for modeling physical situations. Google might use this, or they probably don't use this exact algorithm because they'll probably use something a bit faster, but this is the general idea when you're doing route finding on Google or anything like that, is how can we get from A to B? So, the dangerous bit for me, Dijkstra's algorithm. If we take all our nodes and mark them as we don't know, either null or infinity or anything like that, we haven't been there, we're just going to start with a blank system. We have an understanding of the distance between our nodes because it's a weighted graph, but if we want to get from A to B, we start off with mark the first node as 0 because we're programmers and we know everything starts at 0. From there, we visit all the connected nodes, so these two here, and we say, well, they were one distance away. Yeah? We mark each of those nodes with the distance they are. And once we've finished processing each of the connected nodes, we then mark our first node as visited. Then we go to the next nodes and do the same pieces. So we end up marking, 1 and 2 is 3, 1 and 3 is 4, 1 and 1 is 2, and so on. marking as we go, because as soon as we've marked something as visited, we're not going to change its score anymore. And as we've done that, as soon as we found the end, at some point with that breadth first search, we have found the shortest path. Now, we found the shortest path in getting there in terms of our hops, but if we have competing paths that are weighted, we probably want to actually figure out which is the best way around. So we have these scores. This is a minimum of 3. So I kind of skipped over earlier, but if we're at this depth and we're marking the connections here, when we go to the next depth, you can see 2 and 1 goes to 3. So we override that 4 as we go in, keep it up to date until we visited, then we're locking it down. And what we can then do is say, can I find the lowest score of the weight and the total value there? So 1 and 4 is 5 here, 1 and 3 is 4 there, and start following it back. So we start off at B and work our way back. So 3 and 1 is 4 versus 5, so we've chosen that. Now this is an interesting one. We might look at this with our human minds and go, well, that's obviously a bit closer, but that 3 is a bit deceptive. So 3 and 1 is 4, 1 and 2 is 3, so we want to go this way. Up here, we haven't visited this node, so we can discount it. 2 and 1, and work our way back. Kind of makes sense. If not, there's a whole Wikipedia page about it that I may or may not have understood properly. So we'll go with that. Yeah, it makes total sense. Yeah, if no nodes with a score are left and we haven't found the end, then there's no path. So if we haven't been able to find our way to the end, then there's no way to the end, because that's how it works. Anyway, taking that, what we can do is we can take that approach, and because it works on a small graph, we can apply it to a large graph. So this map of London, we can go through and calculate. I know some of you won't be able to read the numbers, but trust me, they're real numbers, as we go through and work up the scores. And once we're there, we can find our route back. So you can see the kind of the wave front of the depth of the breadth first search going through. If my clicker wants to work, and then we can work our way back from there. And like I was saying, this is the kind of idea that Google brings to the table when they tell you how to get from A to B. What's really interesting about this is it's great for modeling physical systems, anything that's quantitative. Yes, it's great to put those numbers in, but what you can also do is weight things in a way that isn't just how far is it from here to there. You can also say, well, how pretty is it from here to there? Like give it a score out of 10, where 1 is the prettiest and 10 is the ugliest part, or crime numbers or something like that. So you can find the prettiest route between A and B, or the least crime bit between A or B, or if you're the police, the most crime, I guess. And we can even use those IMDb ratings to actually find, well, hang on, we don't really like After the Sunset, so maybe we could do a hop through another film because that's rated 6.5, and we want at least 8. Or going by the worst movies. What's the worst thing Kevin Bacon's ever been in? Answers at the end. Who likes trees? Yay! Hey, I didn't say you had to answer. Trees, not the wooden things, but they're a special kind of graph. So if you worked with trees before, not necessarily with the kind of bigger structure, you'd recognize those nodes. But instead what we have are things that basically represent upside down trees, if you represent them as hierarchies. They are an example of acyclical graphs. So if you look at this, there's no way you could keep going forward and find yourself looping back here. You have to backtrack to get back to a node you've already been at if you're going to. And these can be unidirectional, bidirectional, and so on. These are called the leaves, and that's the route. And hopefully we've all kind of encountered concepts like that before. So yeah, there's only one path between the two nodes, and it's acyclical. Can't go around. What's really cool, I really like this about trees in general, but have you ever As a kid, or even now if your drawing skills haven't improved like mine haven't, you take a Y and you draw a Y shape. And then you take the ends of the Ys and you draw another Y shape. And then you take that and you'll get a tree. It might be a very similar tree to all the other ones you've drawn, but you'll get a tree like that. And what that is an example of self-similarity. So you can see how our big tree, our forest is what it is constructed of many different trees as we go through. And the cool thing about that is anything we can do to the little one, we can do to the big one. We can apply our algorithms at any lower scale. And we can do that with graphs as well, but with trees, I like that. Mainly so I can make a point about liking trees. Who was in James's talk yesterday? James Tickham, about climbing the abstract syntax tree. Cool, you can fall asleep at this moment, or if you didn't follow this bit, then please don't heckle again, but refresher time. How many people have ever used one of these? Like specifically this type of calculator. So this specific model, my dad had one of these, and as a kid I loved it because you press the button and they go click, and now that manifests itself for other people in those mechanical keyboards that keeps everyone else awake at work. But what it did do was it didn't accept it in 1 + 2 = mode. Instead you had to put it in what's called reverse Polish notation or postfix. So it's counterintuitive. We write down on paper 1 + 2, but we have to put into this because of memory restrictions and not understanding natural arithmetic. This early kind of calculator, you had to put in those numbers in a different way. And it's rooted in the way that computers process arithmetic. So hopefully everything I say today and right now will not contradict Mr. Tickham from yesterday. Fingers crossed. So here is a stack. Here's an example of reverse Polish notation. So we have our operands and our operators. And the way it works is when we take something written in this kind of, I mean, I can't look at that and explicitly work out what it is without a lot of thinking. We keep putting our operands into a stack until we find an operator. For the purposes of this, they're all binary operators. So we find a plus, we pop the top two out of the stack and apply our operator and get a result, 11, and we put that back into the stack. And then we carry on. We've got a 3, we put that in, and we hit our multiplier, we get to 33, and put that in, and that's the end result, and that's how we get through to that. But the thing is, well, sorry, I'm skipping ahead of myself. The great thing, as James pointed out yesterday as well, damn him, was this also is really good for operator precedence because it's built into the structure. The way it's presented means that there's no way you can get confused as to whether you should do multiplication or addition depending on where things are in the sentence, in your mathematical sentence. So, we can't read that. But we can't really read that either. No? So the answer to how do we get between these two things here is trees. Of course it is. Having taken that in, if we take our operators as nodes, just like in our abstract syntax trees, we can then walk through this structure and follow everything around in a way that will produce the output. So we have 3 ways of walking a tree. We have pre-order, in-order, post-order, or prefix, infix, postfix. So with pre-order, we go with the node, left child, and then right child. If we go to a left child and it has children, we go to the left child of that, and so on. And we can see, as soon as we hit a leaf, write it down, then head back up the tree. So going down there, we write our node in pre-order here. We then head down, write our node again, right child, and so on, all the way down, and we can just circle around the outside of the structure in our graphical kind of approach here. and come up with what I assume is a particularly useless piece of arithmetic for our purposes here. But that's one way of writing something that's... Does anyone have a use for this? Sweet. I'm not the only one. Natural order is in order. So where we're writing number, operator number, we want to write left child, node, right child. So 5 plus 7 plus, times 3, and so on as we go through. And then we can hit, the operator precedence is problematic for us here because we haven't encoded which part of the tree has we gone through here. So what we might want to do is every time we descend into an operator, wrap it in those horrible little brackets there. And finally, the post order is producing that reverse Polish notation. So left child, you've got the idea. So how do we get it in the tree in the first place? Well, we went to James's talk yesterday, didn't we? You can use a lexer and parser, or Dijkstra, again, that very clever guy, came up with what he's called a shunting yard algorithm, which makes use of stacks and so on. That again, I think James covered, but not in such a name yesterday. So it's outside the scope of this talk, but look it up, Dijkstra shunting yard thing, if you find any of this kind of stuff fascinating. He's done a bunch of stuff on this, and I personally really enjoy it. And that's why I'm up here boring you right now. Who's used to nested sets? Cool. Okay. A problem is, those trees, we can look at trees and think menu structures on websites. You know, we've got a top-level menu, and then when you hover over that, you've got items underneath and so on. Or you might have a map of things. How do you take that and model that in a database? And the answer is use a GraphDB, like Neo4j. Hipster overload. Not really, we're just scared of new things. Yeah, seriously, if you're going to model a graph, use a graph database. But if you don't have a graph database, or you're just masochistic, like I can be at times, how do you store it in a relational database? Well, easy. You have an ID and a parent ID, and every a root with, or a record with no parent ID is the root. It's the one at the top. So that has no parent, so that must be where we start, and the upper level, and then this one has a parent of that, and so on. And I'm sure that most of us encountered that in our databases day-to-day, how to store these things. The problem is, how do you find all this bit here? Or rather, all these parts here? Well, you get that node's ID, and then you find all the nodes with that as the parent, and then you find all the nodes with that one as the parent, and then you find all the nodes with that as a parent, and you find all the nodes, and it's, you know, you've done 1, 2, 3, 4, 5 database operations just to get the whole tree, which isn't the most efficient, and will be wasting time and resources and everyone's money, and we don't like that. So this is where nested sets come in. Now, nested sets themselves are born out of set theory, and I'm going to try to describe something to you because I couldn't figure out how to actually put it on the slides at the end. But first off, how do we do that with the trees? So if instead of just having that parent ID, we also have a left and right column against each of our records, they're just going to store numbers. They're just going to store integers as we go through. What we want to do if we want to store this is we walk the tree. We walk it from left to right as we have, and we just descend down. We start with 0, and as we walk around this graphical structure, or as we descend in, as we encounter a new node we've never hit before, we give it the next number in the sequence. If we've encountered it again because we backtracked, we put that number, instead of in the left column, which I should have said a second ago, you put it in the right column and store that. as we walk down, you can see at the bottom we have the numbers close together, but as we around the top, they're a bit further apart. So does that make sense? Yeah? So as you walk down, as you first encounter a node, set this counter 1, 2, 3, 4, 5, 6, and so on the left. And as you backtrack back up, as you walk back around it, you set it on the right. And what that does is, that allows you to have a parent has these values that encompass the values underneath. Yeah? So if you want to find the children of this node here, you just select from the nodes where the left value is greater than 1 and the right value is less than 6. And that works for any part as we go. 8 and 15, so 9 to 14, left and right. If we want to insert, it's a couple of separate and easy operations. Now that we've walked the whole tree a first time, that's assuming we didn't, we had to start off with a tree we hadn't stored in this procedure before. We just attach it as we would, take the values of left and right from the parent we're attaching it to, set the left of the new one to 1 plus the left of the old one, set the right to 1 plus that, and then update everything, update the left and right of everything to the right in the graph, to the right in the tree. Kind of makes sense? And again, deleting. I thought I did delete in there, but you can do delete with updates. So you remove it out to the tree and don't document it for people so they can't follow what you're doing. Whew. So what you should really be doing, though, once you've done that, is you should then look at Doctrine or Propel or Eloquent and find the nested sets implementation in there. What I haven't been able to put on the page is the normal way of representing nested sets is by showing Venn diagrams and having an overall view of everything in the set, and then within the children of that, you have everything within there. So you might have this node here is represented by an overarching set, then this node here is a smaller node in there, and so on, and a view there. And the fascinating thing I found that I can't actually put on paper because my imagination is shot, is take this structure, think of it in your mind, just picture it in three-dimensional space. You've got apples and string, or rocks and string. So hold it from the top in your mind, from the root. Now, slowly drop it down, look over the top, and all of a sudden, what you've got is a representation of that nested set side of things. If you look at the whole as you look over the top, if you look at the representation of that with the numbers going 0 to 1 to 2 and so on, you can see that from over the top. And now I bored you all. I want to come to the conclusion of my talk, which is graphs are cool. Thank you. Yeah, I shouldn't have front-loaded the headline generator there, so feel free to play with that in the 5 minutes we have left. But if you've got any questions, then please do fire away, Gon.
So what is the worst Kevin Bacon?
What is the worst Kevin Bacon movie? That, my friend, is a journey to self-discovery that only you can make, but it's probably Pyrites. Although I'm pretty sure there's worse. Any other questions?
Are you seeing people implementing graph databases alongside their existing database backends?
So the question for the playback is, are we seeing people who are using graph databases alongside relational databases? Not directly. I imagine that it's quite a tough sell to have two different databases in the same organization. But when you do, you can get the advantage of using both. Graph databases, like document databases, aren't great for some of the relational stuff that we use relational databases for, but they have their own purpose. So a really good example of a graph database might be, or an application of it would be a social network. So the idea that you can have anything connected to anything else by a known relationship. This person is a friend, this person is an enemy, they're a friend in the other direction, you've got bidirectional kind of connections there. So, so having them alongside to fulfill a separate purpose. You might have a graph database that models the structure, and then you might want to back it up with a relational database. But in terms of combining the two, I've personally not seen it, but I can't imagine why you wouldn't want to, when the advantages of just flowing along from a single node and finding your way throughout the organization is one thing, but actually having a nice relational protected system there as well is pretty cool. Yes?
It's not really a question, it's more an answer.
Yeah.
We do use both of them.
Oh, you do use both. In which case, yes, I see people use them in the front row.
And it's very useful.
Yeah.
We're using them to for different sets of data, related with each other, of course. It's like, but it's very useful.
So you use it to
Neo4j.
Neo4j and MySQL. So you're connecting different sets of data together with the graphs,
Yes.
and storing more relational stuff in MySQL as you go there. Cool. Maybe next time you could give a talk on graphs. Anyone else? Sweet. I can get out a little early, and so can you. You can beat everyone to the free. Oh, it's decided to give up now. Cool. Well, you can find me. Email, chris@choult.com. Twitter @choult. LinkedIn, Christopher Hoult. Find me on joined in with the QR code that very few people use, but if you do, great. It's easier than remembering these pieces of code here. If you do want to talk to me as well, I look like this, and I do reuse my jokes. So yeah, thank you very much for coming along.